So today is our fifth session, and today we will be discussing briefly about logistic regression, that is the cost function and gradient descent function, how it operates on the basis of the loss function that we had discussed in the previous class. And thereafter we will be discussing how you actually operate using your cost function to update your weights and bias such that you can optimize your model. So firstly, I would like to ask you guys that on the basis of previous lectures, have you been able to understand anything about gradient descent so far?
Yes.
So could you elaborate in very simple language? What do you understand by gradient descent?
It is an optimization technique.
Mm-hmm.
We derive the derivative of the cost function and we try to deduct it from the coefficient in each of the iteration. And thereby we try to get the lowest the lowest function, the lowest function which is very optimized. So that is how we try to, that is what is the gradient descent.
Right, right. So if we have to put it simply, then gradient descent basically means that your cost function, essentially, you have to bring it to the minimum possible value, or at least in close proximity to the minimum possible value. Now, what do I mean by gradient descent is, you have a function, right? You have a cost function. The summation of your loss function gives you your cost function. Then we can basically write it like this.
Yeah.
Okay, so if you can follow this representation, then that means your cost function can be expanded into this. It is nothing, I've just substituted the value of your loss function, which I took it like this, and this expanded form I have substituted here. And now instead of a single y, we have yi, because we are talking of the entire data set now, from 1 to m, whatever is the number of data set. So this is the summation of your whole cost function. Now whole cost function, basically if you want to minimize, so any given function if you want to minimize, then what is the first step that you do?
Take derivative.
Take derivative.
Take derivative.
Right. So when you take the derivative and you equate it to 0, in this case, the weights and bias are the parameters associated with the function. So you get equations which include these parameters. So essentially, when you say you are taking derivative, it is nothing but your gradient of the function that you are taking. Clear so far? Where does the term gradient come from?
Ma'am, please repeat the last sentence again.
In order to minimize your cost function, you basically take the first derivative of the function, the cost function, and you equate it to 0. So this derivative, this first derivative of the cost function that you take is nothing but the gradient of your cost function, right? The first derivative is also called as gradient. Suppose this is my cost function.
Ma'am, you are trying to say we are naming it as gradient because ultimately in gradient we are trying to minimize the cost.
Yes, we are trying to minimize the cost function. Suppose this orange curve is your cost function. Then at any point, if you want to find the tangent of that curve, it is nothing but the differentiation at that particular point, isn't it?
That's correct.
And that's the gradient you're talking of. Suppose this particular point, if I take, then this tangential line, the expression of this tangential line is nothing but the gradient of this curve at this particular point.
Yes, ma'am. Yes, ma'am.
Okay, so if that is clear, then we move ahead. What we are talking as descent, your downward movement. Consider I put this cost function at this particular point, any given value of my weight and bias. I randomly just initialize it at any given point. So what do I want essentially? I want to take incremental steps such that essentially I reach the minima of this function. This is my aim. I want to initialize anywhere in this curve and I want to move downwards such that that is the minima of that function. So whether I initialize here or I initialize somewhere here, I want to move downwards till I minimize my cost function. This is the minimum value of your cost function, right? No other value can take its magnitude.
Yeah.
Okay, so if that is the case, then whether you start here or here, you need to define something, some equation, such that you can move downwards at some specified rate till you come downwards here. So now let me give you an example. Let us consider the scores of a certain examination are declared. Okay, and you come and ask your friend, hey, what is the marks that you got? And your friend asks you to guess. So you give an initial guess, say suppose 60. Okay, so he says, okay, no, not really 60, less than that. So what is the second guess you can do? Say suppose you say 40, and he says, no, more than that. So what is the range that you are talking of right now?
Third prediction will be 50, kind of.
Yeah, somewhere between 40 to 60, not beyond
Yeah.
that range. So you've constricted your range, right?
Right.
So now you give a third prediction and he says maybe less than that or more than that, and accordingly you take a fourth prediction. That is what you're doing, right?
Keep on reducing that range.
You are keeping on reducing that range, exactly. So if that is the case, then if you take an initialization anywhere, suppose here, then if you increase your weight or whatever parameter is in the x-axis here, in the horizontal axis, if you increase that, then if the cost function also increases, then what are you supposed to do?
Do not do that.
Don't do that. Exactly. That means where is the point? Left or right? Which part of the curve is that point? I took a random point anywhere on the curve, and when I increase the weight, then my cost function also increases. Where can it lie in this curve? Left side or right side?
Right side.
Right side. Exactly. So if that is the case, then what are you supposed to do? You are supposed to go backwards. Not going to add it up, you're going to subtract it downwards. You have to choose the path in which your cost function decreases, not increases. Okay. Now suppose, consider I took a random point, and upon increasing my x, or whatever my whatever is my x-axis, whether it is weight or bias, whatever my parameter is on the x-axis, if I increase that, then my cost function decreases. Then what am I supposed to do?
Increment.
Exactly. So you're supposed to increment. Now that is what this represents essentially. This is the new weight and this is your old weight. Existing weight. Okay. So you take your new weight and you modify. This is the modification sign. A colon with an equal to. You modify this weight. How? You take the weight, old weight, and subtract it with your learning rate, that is alpha. Alpha is nothing but how fast you are incrementing or decrementing. How many steps you want to take or how fast you want to move downwards. That is your alpha. And that determines how fast you will be able to optimize your model. Okay. So this parameter is called learning rate, and this is the derivative that you took with respect to your weight. This is the partial derivative. See, your cost function essentially dependent on your weight as well as your bias. Now with respect to weight, if you are considering, then you are taking the partial derivative with respect to weight. When you are modifying the bias, then you are taking the partial derivative with respect to the bias, keeping weights as constant. So that is how you achieve this. So if you are modifying the weight, for example, then if it is somewhere here, then your slope is a negative value. If your slope is a negative value and there is this minus sign, so essentially you are adding this value to the old weight. So basically you are moving forward. On the contrary, if your point is somewhere here, then if you compute the derivative, then the derivative is a positive value. So if that is a positive value, then with the negation sign over here, you basically subtract the value. So you basically move downwards, backwards, right? So in either of the scenarios, with the help of this equation, you will be able to come to the minimum value. Say suppose if you have to come to, suppose this value is 2.5. and you take alpha as 2. This is 8.
Mm-hmm.
Now, if you from 8, in steps of 2, if you minimize, then from 8 you come to 6. Then from 6 you come to 4. And from 4 you come to 2. Now, if you subtract further, then it comes to 0, which is somewhere here. So you've moved away from your lowest value of cost function, whereas the lowest value was 2.5, right? So it is not just that you take a very high value of learning rate and you go ahead with the model so that you get a speedy optimization. You may even miss out on the optimization. So this has to be played with. This parameter needs to be played with such that you get a value close to your minimum value. This is somewhat like trial and error, but with experience you will be able to understand what is the optimum value of alpha that you can choose, or close to optimum value of alpha that you can choose, such that you can associate it with the data points and the model that you are dealing with.
Okay. So, ma'am, like the minimum cost will be derived from the derivative that you explained earlier. When you would be knowing the minimum cost, then you would keep on reducing the point using some rate, and the rate can be based on your experience or your knowledge. It could try to keep it as small as possible so that you do not go down the minimum value.
If you keep it as small as possible, then it may take a long time to optimize your model. So basically, it has to be in relevance to the model that you are training and the data on which you are training.
Correct. I got it. If you are talking about some data where you believe that the rate should be, say, 100 miles per hour. If we are talking about, say, rocket that travels, say, millions of miles, so then reducing 100 miles might be very small, or maybe like optimal. Okay. So what I was saying is, Soumya ma'am, if I try to understand it, if the distance we are, say, for example, in our ML model, we are talking about millions of miles, then probably 1,000 miles can be a good optimal value. But if you're talking about, say, 100 miles, then 1 mile can be a good optimal value.
Exactly. So it is relative to the model that you're dealing with and the data that is associated with it.
Got it.
Right? So it comes with experience.
So ma'am, is there any rule of thumb for this to select the optimum alpha value?
Not really. It is just hit and trial. So you can maybe take 100 times a smaller value than your range of data, and that could work probably, because it is relevant to the model that you're discussing. In general, if you want to talk, then maybe a fraction of hundreds of the span of your change, that would probably serve your purpose. So if you're dealing with, say, here the difference is of 2, so maybe 100, when you divide 2 into hundreds parts, then probably that would be a good learning rate for this kind of data.
To avoid overfitting by choosing our optimum learning rate, because we have to take care of the overfitting also here, right?
No, learning rate does not affect your overfitting or underfitting. That is dependent on the model. Here you are selecting a model and then you are minimizing your cost function. I specifically mentioned in the last class also, the concept of overfitting and underfitting comes only when you're comparing amongst different models, not when you are talking of one particular specific model as such. So when you're pinpointing that, okay, this is the model that I'm going to use, say suppose a linear model, or say suppose a parabolic model, or whatever kind of model that you're fitting it with. So you've chosen your function already. So now when you have chosen your function already, you just have to minimize your cost function such that you optimize the fitting of that particular function to the data set that you have. It's basically regression.
But this learning rate is also applicable in neural networks also. No? So this the same logistic regression is being used there.
Mm-hmm.
So I was relating that how to select optimum epochs in that case, but that is the another topic. Just I want to interested to know that how to select the optimum learning rate here. That's it. Okay.
There is no such rule of thumb, but people generally take hundreds of fraction of your difference value. normally.
Read it somewhere that it is based on your experience. So once you start making such kind of like adjustments, you would get to understand that your learning model, last time my learning model took more time when I choose a smaller rate value, and this is a similar data, I should change little higher value. So something like that. It's all based on experience.
Okay, sir. Thank you.
And probably now you understand what you mean by gradient descent, right? You take the gradient of the cost function and you descend downwards such that you come to close to the minimum cost. Now, it is not always possible that you may exactly come to the minimum cost value, but somewhere in close proximity of the minimum cost value. So when the difference is so less that you can actually, ignore that magnitude of difference, then you can say that, okay, I've minimized my cost function and this is the optimized function that I'm going to use, or this is the optimized model that I'm going to use. Okay, so when you're talking of a particular model, you have to optimize the weights and bias, and this is how you optimize the weights and bias associated with it. Okay, the simplest.
In general, ma'am, in general, that do we keep a check of like whether I'm overrunning it or not? Like greater than 0 should always be there, something like that. I mean, greater than cost value should always be there. Minimum cost value, greater than minimum cost value, always.
Sir, actually, when we are increasing the weight, the cost is reducing, right? And at certain point, the cost in weight is perfectly matching. But ma'am, Soumya ma'am and you, sir, if there is a negative cost is coming, is it possible to reduce the weight then?
Then you take the previous iteration, basically.
If
you come to the point where your cost function had minimized, and then in the next iteration your cost function is increasing, so basically you feed an algorithm to your machine as such where it is supposed to stop. How will your algorithm know that where this iteration, this loop has to stop? This is the condition that you feed.
Exactly.
This is the exact condition that you feed.
Awesome. Got it.
Yeah. What will be that condition?
This will be the condition that you're going on descending and your cost is minimizing, and in one particular iteration suddenly your cost increases. So when that happens, it basically stops and takes the value of the previous iteration.
Yeah.
Otherwise you cannot count how many iterations you're going to give. If that was so certain, then what is the point of doing this whole exercise? You're doing it because you don't know where it will minimize. You don't know how many iterations it will take, but you do know that whether or not, what is the end result you want or expect.
Okay, can we say like this, madam? This is Dr. Suryanarayan speaking. Am I audible?
Yes, please go on.
Yeah, this learning rate parameter, if we set that is equal to 1 by 1 plus n, n is the number of iterations. Then initially n is 0 during first iteration, then learning rate parameter will be 1 by 2. As number of iterations increases, alpha value decreases.
Okay.
So as we reach that minimum value, alpha value will be very, very small.
Right.
Another question somebody is asking is when to stop change of weights. Is generally what we consider is the previous weight minus present weight. If the difference is less than some epsilon we define, then we can stop the iterations.
Yes, so basically that epsilon is nothing but the error, the tolerable range of error that you can associate with the part.
In weight vector.
Yes. So for example,
not in cost function. Not in cost function.
Yes, not
the
in cost
change
function.
In weight. If the change in weight is not considerable, then we can stop training the network.
Okay, so these are like you defined a function 1 by 1 plus m, where the learning rate could be dynamic. It is not a fixed value. So what you're doing is you're basically hastening your model. See, if initially you know that you are at a point where you can take large steps, and as you go downwards you can take smaller steps such that you can move precisely to your value, right? So if that is the case, then if you, instead of defining a learning rate which is a constant value, you could define it such that initially you take large steps and finally you take small steps. That is also represented by arrows over here, as you can see. So that is a process by which you can hasten your speed up your process. and that would lead to lowering of the overall time how you optimize your model. That is essentially the whole idea behind it. So am I clear? Is there any?
Awesome. Yeah. Wonderful.
Ma'am, what the role of bias here?
Like your weights, you also have to optimize your bias. It is also a part of a parameter that you have to optimize. It is not just the weights that you optimize and you get your model. Your model is a lump sum, like a total representation includes terms associated with weights and also terms associated with your bias. For example, if we are dealing with a linear function y equals to mx plus c, then m is your weight associated with your feature vector x and c is your bias. So just optimizing m will not give you the whole equation of the model that you are feeding. You also need to optimize your c, right?
Yes.
How does it ensure that it has reached global minima and not local minima?
The whole idea behind it is we define a function such that it would have just one global minima. If you I think if you refer to this last slide in the last class, then I particularly discussed that we have to choose our cost function such that it cannot have multiple global minima. The cost function essentially has to be something which can be represented something like this.
So, can we say this is the limitation of this algorithm?
You can, yes, you can. So you have to choose a cost function that that particularly has something, some form, something like this. See, it is beyond the scope of human mind to perceive beyond 3 dimensions, as I had already mentioned. So if you're talking of n dimensions, in that case, it is something, a hyperspace that you can refer to, wherein essentially you will have one global minima. You will not be able to picturize it, but then there will be one global minima associated with it. You cannot have something like this. You cannot define a cost function that is something like this. If that is the case, it is very confusing. Then your model will not be trained because you cannot optimize your parameters. There are so many local minimas.
And man, same goes for the multiple feature also. Like this is for two feature, right? X and Y, two variables.
Right.
And if there are 3 or 4 to be categorized,
right,
using
so it works similarly there also. That is why we chose this function. That is why I did not go into the intricacies, but I told you that this function is going to work.
Okay.
Right?
Yeah.
Okay. So, yes. Let us take this example. Now, now that we know the steps, we need to initialize with some random values of your weights and bias, which are the parameters associated with your function. Then you basically take steps to modify your weights and bias or the parameters which are associated with your model such that you basically minimize the cost function, and this you do by the steepest route downward. For example, this for this 2D case, it is very easy to perceive because this is the steepest way downward. But if you were talking of any point here in the space, then it is not that you can take any random path and then go downwards. It will be towards the steepest downward path it will take. This is how this function is defined. That is called descent. If it is somewhere here, then basically it is going to come this whatever is the bisection from this point, it is the steepest path basically because of symmetry, and that is the route that it is going to take downwards. This is irrelevant in the case of 2D, but in 3D you will be able to perceive that.
Yeah, man.
Okay, and then what is the final aim? To converge to the global minima value, or in most cases close to the global minima value, right? Because you are basically estimating the error associated with your function, and whatever that error is, if that is less than a certain designated value, say suppose initially the error was 4, then it came to 0.4, then it came to 0.04, then 0.004. So what is the acceptable range up to which you want to do? Because this can go on, this can continue, right? This is never going to stop. So wherever is your acceptable error range, which you can say is close proximity to the actual value, then you can say that, okay, yes, this is the model which I am saying that it is optimized. Okay.
Yeah.
Okay, so if that is the case, we consider an example. Suppose we have two data sets, a very small training data, basically inefficient, but then this is just an example to fairly understand what this concept means. So you have two data sets, 1 comma 2 and 3 comma 4, and you're fitting a model such that you have a straight line fitted to that model. So if that is the case, then you define your cost function. So cost function is the summation of your loss function. So if this is the form of your loss function, right, original y minus equation of y, that is mx plus c. So substituting the values of y and x from the first case as well as second case, so you get your total cost function. This expression is clear, right?
Yeah, from the previous page itself. If you go back to previous one, anybody can relate it.
Right. So your loss function, you're basically taking the loss function value and you are adding it up for the different terms. In this case, two terms. So you have just expanded the summation and substituted the values of x and y in both the cases. So if that is the case, then now what am I supposed to do? I'm supposed to take, if I choose to optimize C, which is my bias. So if that is the case, then I take a partial derivative of this function with respect to C. And if I do so, in that process, I get a value of minus 4. Clear so far? So with this expression, if I want to substitute here, then how am I supposed to write it? My new C is nothing but my old C minus learning rate multiplied by your partial derivative with respect to C, which is minus 4.
Mm-hmm.
Right? So essentially, from this expression, I want you to predict where was my old C and where is my new C. Considering that my partial derivative with respect to C came about to be minus 4, where over here, towards the left or right, where could this old C be?
Positive side.
Left.
Left. Sorry.
Why do you say left?
Because minus is there, no? So after reducing the cost function, it is becoming minus 4. So obviously it will be something more than that in the negative side.
In the negative side. So if you take a slope anywhere over here, it will be a negative side. Negative. The tangential here will be negative, right?
Mm-hmm.
Tan theta
Show
here.
random value at the negative side.
Right. So it will be a negative value. So it will be somewhere in the left side, my old C. And basically what I'm doing is I'm basically adding the value. Instead of weight, I should have written bias over here actually. So I'm basically adding the value of bias or C in this case, such that I'm modifying. My new C will be somewhere here. If my point was here, my new C will move rightward.
Correct.
Right?
What will be the same? This is the partial derivative with respect to C, right? Bias.
Right.
What if we are taking the partial derivative with respect to weight now? Yeah.
So that is the same thing. Now instead of partial derivative with respect to C, you differentiate this with respect to M and you note down the value of this equation and now substitute the value of X and Y here. Well, it is already substituted. So you basically get a value which is a partial derivative in terms of M. So now if this is a positive value, then your point was somewhere here and you are moving leftwards. If you get a negative value, then the scenario is similar to this case.
How come that only the partial derivative will suffice to optimize the value of the cost?
No, just one partial derivative is not going to suffice for optimizing the cost.
I'm talking about that. Why we are not considering both the factors M and C?
You are doing it individually. That is what I'm saying. This is just one example that I quoted. You also have to follow this up with your optimization of weight. See, I have quoted this equation. This is the entire equation, right? So
yes.
if your weight, this is weight, you can call it as M, and B, bias, you can call it as C in this linear case. If this was suppose a case of parabola, then you would have two weights, M1 and M2, and you would have one bias, C. So your expression would be y equals to M1 x square plus M2 x plus C. So now you have two weights to optimize and one bias term to optimize. Okay, so this part is clear now?
I was asking, we are adding partial derivative to old C. So how it going to be positive? And I have not understood that concept. Please repeat.
Okay. You are not adding, actually, you are subtracting from your old C.
It is -4. So when you will do minus multiplication in the learning rate to the learning rate, it will become positive. That's why it is. She is saying it is adding. So if you see C old minus learning rate into derivative of J with respect to C, right? And if your value of the derivative of J with respect to C is negative, so your multiplication will become negative into negative. Negative into negative means positive.
Yeah, I have understood that part, but ma'am has said it is going towards down. It is going to downward direction. So if it is positive, so how it is going to descend? How it is going towards downward? That I have not understood.
When you are saying positive, you are not talking of the vertical axis. You are talking of the parameters axis, that is horizontal axis. So if you are somewhere here, then your cost function value is somewhere here, the high value, and you are going downwards in terms of your vertical axis, so your cost is supposed to go downwards. But when you are adding, then you're not adding in the cost function, you are adding in the weight or bias, whatever your parameter is, in the horizontal axis. So if you're adding in this case, so basically you are moving downwards in the vertical axis. Moving downwards is associated with your vertical axis. And when you're adding, when you're talking of the parameters that you're adding, then you're talking of this. When you're somewhere on the left side of this curve, then adding here would lead to a downward motion of your cost function. Whereas the case of descent will be true somewhere in the rightward portion of this cost function, when you are basically subtracting your parameter. So the scenario is opposite in both the cases.
Yes, ma'am. So far, so good.
Okay, good.
One doubt, in this example, we have seen the derivative of the parameter is negative. Means it is actually going to increase the cost. So can we have a negative learning rate and get the reduced parameter in terms of cost? Can the learning factor be negative?
Not really. I did not follow your question. Why do you say that the learning rate needs to be negative? Why would a negative derivative value would lead to an increase in your cost function? I did not follow.
Because the new C, if the derivative of the parameter C is a negative value, the
derivative of your cost function with respect to parameter C, right?
Right. If that is negative, the new C would obviously be greater than the old C.
Right, it has to. So, no, okay, your C is not the cost here.
Yeah.
C is your bias.
That's right. Here, when the bias value increases, the cost function value decreases.
Exactly.
That way is confusing, it seems.
Yeah, C, you are confusing it with cost function actually. So that is why.
Yeah, everyone now.
This C is actually your bias, which is your mx plus C, right? Here is your C.
Okay.
This is your C.
Okay, if
here cost function is J.
Cost function is J.
Function is J.
Right.
With the increase in the bias, the cost function would decrease. That is what
when your bias is somewhere on the left side of this curve. In the opposite scenario, when it is somewhere on the right, then the opposite scenario operates.
Okay, right, clear to me. Thank you.
Okay.
Ma'am, one more thing. What is the role of tangent here? You are showing the tangent here in the gradient. As in the
just to give you a clear picture of whether it will be positive or negative. See, if it is a positive slope, then it will essentially be, inclined rightwards. If it is a negative slope, it will be inclined leftwards, right? More than 90 degree, it is going to be, the tan theta is going to be negative. and less than 90 degree, the tan theta is going to be positive, right? So if you're on the right side and your point is somewhere here, if you take a tangent, that is basically the gradient value that you get, right? So from your eye approximation only, you can see very easily that your gradient is a positive value. So if that is the case, then you can directly associate whether you are going to add or subtract. Clarity of representation, nothing else.
Okay, ma'am. What is the role of sigmoid? Okay,
Ma'am, if we take a parameter as weight.
Sorry?
Ma'am, I was asking if we take parameter as weight. So if the same concept goes, if we add a value, in the sense if we get a add up value in weights, so will it increases the cost value as well, or will it move towards that downward direction?
Whether or not it will add up to your weight or subtract to your weight, that is immaterial, but with every iteration it will essentially go downwards. If it is in the left side, then it will add up such that cost decreases. If it is in the right side, it will decrement itself, it will subtract such that the cost decreases. So cost will decrease in both the scenarios, whether you go and add up the weights or you go and subtract the weights. So that depends on where that point lies, and depending on where that point lies, you will either get a positive or a negative value here, and depending on that value, it will modify the weights such that it may add up or subtract, and accordingly it will basically go in the forward direction of your x-axis or the backward direction of your x-axis.
Yeah, got it.
Okay.
I want to try something here. Just one minute only. Okay. So we started with linear regression. We have to convert it into logical regression. Logistic regression. In logistic regressions, we convert the points into some multiple minima situation. You remember we talked about the line which will divide the 2 points, and then we have to find the points which are closer to the line in case of logistic regression. So there are multiple minimas that comes up which are very close to the line, but we cannot go with the multiple minima, so we decided to do a logarithm of that. Logarithm made the curve with a single global minima, and then within the single global minima, we have tried to find out the cost function, the smallest cost, and also adjusted the bias. So that's how the entire learning curves happens.
Exactly.
Okay.
Thank you, sir. Thank you for summarizing these things. Yes, ma'am, you can go ahead with now.
Okay, in that case, we move ahead with the polynomial regression. As someone had pointed in the previous class that they want a separate slide on polynomial regression. So we will basically just go ahead with the derivation part, and the rest I hope you can figure it out yourself, because it is similar to the case of linear regression with just one more add-on. That is, you get one more equation to solve with. Earlier you were solving two system of equations to come upon the values of your two parameters m and c. In this case, you will solve three system of equations such that you can derive the values of m1, m2 and c. And once you have these values, you basically have the whole model. You have this equation. So any polynomial, for example, in this case, we have a 2-degree polynomial. You could have n-degree polynomial. It will follow the same representation, right? So with the number of degrees, basically your, suppose you are talking of n-degree polynomial, then the number of terms in that n-degree polynomial will be n plus 1.
Yes, ma'am.
Okay, so if that is the case, for this 2-degree case, if we have to compute the value of your error function, it will be this value. Not essentially this value, the square of error function will be this value, right? If we consider that root mean square is your error function, then this is what your square of error function will look like. And essentially, if you are talking of minimization of your error function, then you are also minimizing its square root. So it's immaterial. Basically, you want to minimize this function in the most simplistic form. You followed me so far? Because we've had this discussion earlier.
We have already discussed these things.
Yes. So if that is the case, then your y hat I is the predicted or calculated data with regard to your expression, and yi is your actual data from your data set. And the difference is basically the error associated with it. You take a square of that and you add it all up. So basically this summation, if you expand, then this is how this is going to look. Instead of this y hat I, you've just substituted the value of your model, right? So now if you have to minimize this error function, then what are you supposed to do?
Derivative.
Yeah, you're going to take a derivative of that. Now that derivative you can take with respect to how many parameters in this case? How many parameters are there here?
3.
3 parameters. What are they?
x1, x square. No, these are the coefficients. X square, xn1.
No.
3.
X
square,
is the variable.
Okay.
X is your variable.
M1, M2, and C.
Exactly.
M1, M2, and C.
M1, M2, and C. These are your 3 parameters, right? So if these are your 3 parameters, you take a partial derivative with respect to these 3 parameters and you equate it to 0. That is how you will minimize your error, isn't it?
Yes, ma'am.
Yes.
So you take this error value, you take a first derivative. When you take a first derivative, so basically this is your expanded term, right? And you equate it all to 0 individually. And once you do that, you come upon this kind of equation. This is first equation, this is second, this is third.
Clear.
Right. So if that is the case, then from this data set, how many columns you're supposed to make? See, you've been given a column of x and you've been given a column of y. Now, how many more columns you're supposed to add? In order to get these 3 equations, you need a summation of x, you need a summation of y, you also need a summation of xy, the product of xy, you also need the summation of x square, you also need the summation of x cube, you also need the summation of x to the power 4, and you also need the summation of x square y. So all these columns you're going to basically make, and you're going to add them all up, and you are going to substitute all those summation values over here. Right? This part is similar to the previous case, right? And once you do that, you come upon 3 system of equations with 3 unknowns, M1, M2, and C. Now can you solve it?
Yes.
Exactly.
3 equations, 3 unknowns.
Exactly. So now in this case, instead of getting a best fit straight line, what do you get? A best fit curve of degree 2. Now, a similar step you can take for n degree polynomial, and that way you will have n plus 1 equations for n plus 1 unknowns. So that is how you basically come upon the final expression of your model.
N minus 1 degree curve.
Yes, n degree curve. For a n degree polynomial,
Okay, n degree. Yeah,
you get n plus 1 system of equations and n plus 1 unknowns for n degree curve equation. Okay, this part is clear? So it all depends on your computational capacity. Usually, manually, you can probably go up to 3 or 4. After that, you actually have to rely on the computational capabilities, and you could come upon for any degree of your polynomial that you're talking of. So I hope this derivation part is clear.
Will we be asked to compute values for these kind of equations in the exam?
I don't really think so, that you will be talking of polynomial regression much beyond the computational capabilities that are generally available. So that is like very far-fetched to think of. That won't happen.
This is soothing. Thank you.
Yeah, but this is really good stuff, Soumya man. This is basics. Ideally, like these all things can be done through the different algorithms already available in Python. So you don't have to do a lot of these things. They are already like ready-made available. But if your basics are not clear what these algorithms are doing or like these functions are doing, which are provided in Python, your learning is not good. So it's like
exactly.
you
So
are
now
building.
that you know the background, it will be easier for you guys to, modify things. If you want to even modify, go there and modify those functions, or, pre-existing functions. Even that
Yeah.
could be done now that you know the basics behind it, how it operates. So what is suitable for your model. With experience, you will be able to do that. But then this is the basic idea behind any kind of polynomial regression. So whether it is a 2-degree or n-degree polynomial, I hope now that you know how to calculate your error function and take the derivative of that to equate it to 0, you basically know how to come upon the equations which are required for any kind of curve fitting, if it is a polynomial regression.
Yes, right now.
And just a heads up, like the previous case where we were discussing y equal to mx plus c, where m was your weight associated with your vector x, and c was your bias. Similarly, here also, instead of 1, you have two weights, m1 and m2, associated with your feature vector x, and you have a bias c associated with this model, right? So similarly, you could use n-degree polynomial, and you could have n weights associated with that, and you would basically have a 1 by n dimensional matrix which you can use to represent those weights. And if you could put it in the form of y equal to wx plus b form, then you can basically use matrix operations to simplify these calculations. So that is what people do. I hope this background is clear to you guys. So should I proceed?
Yes, this is clear. Basically, what you have done is you've taken out, the error between the predicted and the actual value, and you're trying to decrease, estimate the cost function of that and equate to 0 and get 3 equations, and there are 3 unknowns, and solve those 3 equations.
Exactly.
My question is, can we apply the gradient descent on this equation, polynomial regression?
It is somewhat like gradient descent what you are doing here. Here also you are minimizing the error. There also you are minimizing the error. But unlike this case, there the error is associated with all of the loss functions. Here, that can be taken as a single summation, because you essentially have just one feature vector x. Now that x comes in forms of x or x to the power 2 or x to the power 3, they are all dependent. So it is very easy to compute and you get equations. But if they were multivariable, here you had x1, here you had x2, and so on and so forth, then probably that would be a tedious job to do it this way. So basically you come upon by estimating a cost function, and then you minimize that cost function.
Okay.
So if that is clear, then we move ahead to naive Bayes classification. So does anyone know of Bayes theorem?
Yes, ma'am. Conditional probability.
Yes. So could anyone iterate?
One probability is dependent on the other probability. The formula for PA by B is PB by A into PA divided by P by B. Oh, PB. That's the formula.
Okay, so it is this, right?
Yeah.
Right.
So this is your formula for conditional probability that is illustrated by your Bayes theorem. So I'm not touching upon this. So we will move ahead with the example that I've quoted here. So you can understand how we are dealing with classification using this Bayes theorem. Let us say that we take into consideration two attributes. What are those attributes? Shape, the shape of your eye, and the color of your body. Okay, so these are your two attributes that you are taking, and you want a binary classification to be done on these attributes. So you've 3 attributes for shape of eyes, and you've got 3 attributes for color of the body. And with respect to that, from your available data set, whatever is the population that you are scanning, you count the number of times you get cats or the number of times you get dogs. So for instance, if the eye shape is round, then twice you got cats and thrice you got dogs. Similarly, if the eye shape was elliptical, then 4 times you counted cats and 0 times you counted dogs. Similarly, if the eye shape is large, then thrice you counted it as cats, and twice you counted it as dogs. Okay, so how many times in total on the basis of shape you counted cats? 9 times.
9 times, correct.
And on the basis of shape, how many times you counted it as dogs? 5
Right.
times. Okay, so let us, for the sake of simplicity, assume that when we say yes, then it is a cat. When we say no, it is a dog. Okay, so Y or C denotes the probability of it being cat. So if it is round, then the probability is 2 by 9. If it is elliptical, then the probability is 4 by 9. And if it is large, then 3 by 9. Similarly, if it is a no or dog, then the probability, if it is round, then it is 3 by 5. If it is elliptical, then 0 by 5, which means 0. And large, then it is 2 by 5. Similarly, on the basis of body color also, we've made a similar tabulation. Till here it's clear?
Yes, ma'am.
So far, so good.
Okay.
Clear.
Okay. So now, in totality, from the whole population of your data set, you compute how many cats are there and how many dogs are there. Okay. So your total population is 14, amongst which you counted 9 times cats and 5 times dogs. So the probability it being cat is 9 by 14 and it being dog is 5 by 14. Okay. So this is your available data for now. Now, a new species is given to you, and that has got round eyes and yellow body color. And you are supposed to find out whether it is a cat or a dog. Clear?
Yeah.
Okay.
Okay, so if that is the case, then what do? You have to compute whether it is a cat or not. So if this probability comes to be a lower value, then you basically call it a dog. If this probability comes to be a higher value, then you call it a cat. So let us estimate that this new species which is given to us, provided this new condition is given to us, what is the probability that it is a cat? What is the probability? We simply put in the Bayes theorem. Okay, so the probability that if it was round by given that it was cat, again multiplied by second attribute, probability that it was yellow given that it was a cat, multiplied by the probability of it being a cat, divided by the probability of the new species. So now whatever this probability may be is a constant, whether this is a cat or a dog, right? This denominator is constant, right? Right? So if the denominator is constant, we can represent this as a proportionality symbol, which is proportional to the numerator.
Okay.
Okay, because we just have to compare amongst these two probability, which one is a higher value. So if we have to compare amongst a numerator and common denominator and another numerator and common denominator, then basically we are just comparing the numerators, right? It is immaterial whether or not we divide with a constant value, right? So since if this was the case for dogs also, then we would be writing P D by nu, and this whole thing, wherever you have got C, it will be substituted by D, and the denominator remains constant. So if that is the case, let us write it as a proportionality symbol and just estimate with the with the data that is available to us. So we've just substituted the values from here, from these tables. PR by C, given that it is a cat, if it was round, given that it is a cat, it is 2 by 9. If it was yellow, given that it is a cat, it is again 2 by 9. And what is the probability of it being cat? 9 by 14. So if we estimate that, we get this value. Again, similarly, if we were to compute for dogs, then this was the value.
Yes.
Now, from these figures itself, what do you think? What is the estimation?
Cat.
It's a dog.
It's a dog, right? 0.03 and 0.08, if you compare, then basically this is higher, right? So the probability of this attribute, if this is the combination of attribute that is given, then there is a high probability that it may be a dog. But then when we are talking of probability and there are just 2 scenarios, then do you think then adding them all up is going to give you 1?
Yes.
You add 0.03 and add 0.08. Does it give 1?
No, it is not going to give.
It's not going to give. Why does it not give? Because you've just taken the proportionality. You've not taken into account the probability of the new, because you don't have this value, right? And it's immaterial because you just have to compare the numerators, because the denominator is same in both the cases. So if that was the case, what we go ahead with is we just go upon by normalizing. What we do is we take this value and we divide the summation of this and this. Similarly, in the second case, we take this value as the numerator and we divide it with the summation of this and this again. So the denominator is same in both the cases.
Making it simple would be 0.031 divided by P nu, 0.08571 divided by P nu.
Right.
This is the answer. Then you can say that, okay, now P nu is same, that's why it does not matter. Since 0.031 is lower, so it's like less probability of cat.
Yeah, exactly. So you could do that, or you could directly normalize it and give the exact value of your probability. So now if you add it all up, it is going to add to 1. So now it is immaterial whether you substitute the value of P nu or not. You will be able to compute this probability. You don't need the value of P nu, because normalizing will essentially give you the actual probability of it being cat, provided this is the new condition. You don't need the probability of the new condition, even though for estimation of this value, you need PB. Here, this value could be estimated just by normalizing, if it is a binary classification case. If it is a ternary classification, if there were 3 columns here, there was cat, there was dog, and there was also horse. In that case, you are supposed to use 3 terms here. And in the denominator, then you have to add 3 terms. And those 3 terms adding together will give you the total probability as 1.
Yeah.
Right?
Yeah.
So this part is clear why we are going for this normalization.
Got it now.
Right? So now it is clear that say suppose this is 0.27, so it is approximately 0.3 and this is approximately 0.7. So I could say that the probability of it being dog is almost more than double the probability of it being a cat. So now you are also giving a magnitude associated with it. When you say 0.27, it is basically 27%. When you're saying 0.73, then it is basically 73%, right? So when you're saying the probability of it being dog, provided that this is the new condition, then it is approximately 75%, almost 3 times in fact.
Yeah, 3 times. Correct.
Yeah, right?
Yeah.
So now you are also getting, on the basis of normalizing, not just this, you're also getting the magnitude. Directly from here, you cannot give the magnitude. Followed me so far?
Yes. What you're telling is this can be extended to this can be implemented not only in binary classes, but also on multi-classes.
Yes,
so that is what you're trying to tell? You said we can take other example.
Yes, of course it can. That is what I'm saying. Probably if it was a binary classification, it is easier to solve. But if there is a third term, then you just have one additional term to add on here and one more expression to add on here. That's all.
Okay.
It works.
Ma'am, what we are evaluating is the probabilities. Okay.
Yes.
What if the evaluated probabilities are not equal? Maybe they are very close to each other. Mm-hmm. So what would be our inference on the output?
So then your model is not capable of predicting. Say if it is 50-50, then your model is not capable. This data is not sufficient, or the model is not fit enough to differentiate on the basis of existing data that you've provided, that whether it is a cat or a dog. If it is exactly 50-50, if there is slight disparity, then the model can say, on the basis of ground rules that you've set, that if it is more than 0.5, then even if it is 0.51, then it is going to call it a cat or a dog, whatever that class may be, right? So that is how it is. But the real life scenario does not operate as objectively as because the training set is limited, right? It is not infinite. So if it is limited, on the basis of limited data, if you're getting a value of 0.51, then essentially it is close to 0.5, and that would probably mean that the model is should be confused. So there is an error value associated with it that you may feed to your model that would basically, if it is in the range of 0.4 to 0.6, probably then also it would call it as confused. It would give a result something like that.
Okay.
Wonderful answer, ma'am.
Is this just only for classification? This is only for classification?
Yes, this is specifically for classification, not regression.
Thank you.
Okay. So now coming to the elaboration why it is called Naive Bayes classifier. So you need to understand that this classifier essentially assumes that your input variables are basically independent. So when you're talking of this case, then it is, you can very easily associate this and this as independent. You don't have to worry about it. But for example, consider a classifier where you are using the keywords or maybe the color of your text background or your color of your text, font size or font shape or whatever it is, and you are trying to classify whether that mail is a spam or not. In that case, using words independent of each other, for example, if there are multiple attributes, like if there is appearance of the word dear, or if there is an appearance of the word friend, if there is appearance of the word call, so you're basically counting on the basis of available data that how many times in a spam mail you're getting these words, and how many times in a non-spam mail you're getting these words. And on the basis of that data, now you are trying to classify whether or not that new mail that has arrived is a spam mail or a regular mail. So here basically these words are not independent of each other. Many a times it may so happen that there is a certain aspect where the sequence of word also matters. If it is, for example, dear friend, then probably that is a regular mail. It probably does not consider the sequence associated with it. So if there was something like friend dear, then probably that would be a spam mail. That is more likely. So in those cases, this is just a very vague instance, but you can assume that these interdependency of the attributes that you are talking of is not considered in this classification. See, here there is no association of this attribute and this attribute, so it works fine for this kind of classification. But there are so many other problems wherein the attributes are not independent of each other, right? So many a times those things impact the results that we have. But then again, for simplicity, if we say, then with a reasonable amount of accuracy, basically it is able to detect whether or not it is a spam or not spam mail. So considering these also, since this classification works fine in most of the scenarios, it is used, and that is why this is called Naive Bayes classification. So if you basically take into consideration these factors, like the string of words, the interdependence, or the order or sequence of the words, or maybe the grammatical sense that it is conveying, so it is going to add on to the complexity of your model, right? So those complexities would basically add on to your computational cost also. So that is not very, in most cases wherein this model works fine, so it is just taken as it is not modified for these complexities, and it works fine with very less computational expense. So that is why people usually go for this kind of classifier, and that is why this term is given to it. I hope you know the literal meaning of the word naive, right?
Yes, ma'am. Newcomer,
Inexperienced.
Yeah, inexperienced. Yeah, that is more descriptive. Yeah, so that is what it is, right? I hope I'm able to elaborate why or how this model works, and well, what are the limitations of this model. Is this part clear?
Clear, ma'am.
Yes, ma'am.
Okay, so with this we will conclude today's session. If there are any more doubts, kindly let me know.
Ma'am, what are we going to cover in next session?
Yeah, we'll do questions.
Actually, I was thinking of going with the assignment questions, but then it totally depends on the choice of the audience. So if there are particular topics that you want to suggest, then I'm open, all ears.
There are two things that I wanted your help on. Like one was like if you can have help with the session on Bayesian network. The explanation that Madam gave somehow was not very clear in some areas for me.
Okay.
I'm not sure for others if it is the same, but if it suits everybody, and brief explanation on Bayesian networks. And second, if you can come to the week 5, that is because I found it more challenging than the previous 4 weeks. So if you can start taking up the topics of week 5, it will be very helpful.
Okay, taken a note of that.
You can take up the multi-layer neural networks. Week 6 is also released.
Sir, before neural network, if we discuss random forest, it will be more appropriate because SVM and random forest are more closely related.
I'm fine with that either. I'm fine.
Yes. Random forest will be more appropriate and it will cover some of the glimpses of decision tree also. We already have the background knowledge of decision trees, no?
Sure.
So random forest will help us to understand random forest.
Okay.
So random forest, okay. And then assignment also, ma'am. We will take up like assignment also. Some question of it.
Okay. So assignment. Which assignment do you want me to discuss? Any particular one, or should I go serially?
Ma'am, can you solve week 4 assignment question? It has been marked already for week.
Okay. Week 4 also noted.
Actually, I'm not able to solve the question number 9.
I was asking, in Naive Baye, we want features should be independent of each other. If they are interlinked with each other, then it would be spam. So,
not really. No, we don't want our features to be independent. It is not something that you can want. It is dependent on the data that you are doing. You're dealing with, and not just the data, the kind of parameters that you're using, and the kind of model that you're dealing with. So I just said that it is a limitation of your naive Bayes classification that it does not take into account the dependence. If there is any dependence, then it does not take into account that dependence of the attributes that you are dealing with. So that is why it is called naive, because these considerations are not taken into account. It assumes, for the sake of simplicity, that it is independent, whether or not it is actually independent.
Got it.
Okay.
Suppose dear and friend, two variables are there. They may be dependent, but naive does not assume that. Naive just works on dear separately, friend separately.
Yeah. Okay, ma'am.
Thank you, ma'am.
Okay.
Have a nice rest of the day.
Okay. Same to you.